Yes? No? Okay. I'm going to assume that it's okay. Hello. So welcome to the first ever NeuroTechX webinar. My name is Sydney Swain Simon, and I'm going to be your host for today. So if you've never heard about our organization before, NeuroTechX is a nonprofit organization that does international community building to help and facilitate the advancement of neurotechnology. So we focus on open and accessible neurotechnology, maybe compared to some of the other communities that are out there. And as a community, we've helped to innovate in the domain through a variety of different projects. We have had contact points with over 11,000 people worldwide, and collectively we've done over 150 events. So you can kind of see all the different locations where we have chapters where if you yourself are interested in getting connected, you have the opportunity to do so. So why are we doing webinars? Because we are such a large international network, the goal of these webinars is to give people from different countries and different disciplines a chance to learn about different subjects related to the technology. We'll be doing these webinars on themes like VR and EEG, as well as showcasing some of the amazing projects and research that we do collectively as a group. As mentioned, this is our first webinar and it's a work in progress. So if you have any feedback, please let me know either by emailing me at sydney@neurotechx.com or messaging me on our Slack. With that in mind, we have 3 things that you should know for our webinar. Number 1, be respectful to those in chat. If anyone is being disruptive, I'm going to be keeping track of everything. I'll be modding the chat. So if anyone is being disrespectful, you'll start by first getting a timeout, and then eventually you'll be kicked off. If you have any questions, please post them in chat. I'll be monitoring it. So the chat function should be found on the right side, so you can essentially put your questions there, and I'll keep track of what's being said. Final thing, before we get this started, if you are interested in doing your own NeuroTechX webinar, please email me at sydney@neurotechx.com or reach out to me on Slack. We're always looking for more people to contribute their projects and their research. So please reach out if you have something interesting to share. So with that, let us jump into our first webinar, EEG Notebooks, an accessible, affordable, and scalable cognitive neuroscience research platform. So with the rise and low-cost consumer EEG devices, has made it easier than ever for students and enthusiasts to access neural data. However, paid-for-access licensing and a lack of beginner-friendly tools has led to frustration amongst potential newcomers and restricted the use of these devices as research tools to those with programming experience. EEG Notebooks aims to address this problem by providing an accessible, reliable, and open-source framework for performing EEG experiments with Python and Jupyter Notebooks. The project is being debuted this year at a number of high schools in the Toronto, New York area, where it is being used as a platform to provide hands-on neuroscience, psychology, and scientific computing education. With the support, contributions, and extensions from the NeuroTechX and the broader neuroscience research and education communities, this project hopes to develop much-needed bridges between research, education, and technology sector. So this will be presented by Dana Morrison out of our Toronto chapter. Dano holds a master's in neuroscience from the University of Toronto. He has 2 years of experience building applications for desktop, mobile, and web. After leaving the lab, Dano decided to shift his focus to the emerging neurotechnology industry and built EEG 101, an interactive neuroscience educational tool for Android that makes use of real-time EEG data. So with that, I'm going to hand it off to Dano to talk a little bit more. You're up, Dano.
I am. Am I on? Hey, everybody. Dano, thanks for the introduction, Sydney. I think that covered a lot of it. I'm just a neuroscientist and software developer now who's kind of found a lot of passion in trying to get others, who maybe are neuroscientists now or maybe even like high school kids who are just interested in this stuff, getting those kind of people able to do the kind of things that like neurotechnology promises like scan the brain and detect emotions or detect different like features of perception, so you could drive brain-computer interfaces. All that stuff is really close to being easily accessible. There's just this kind of implementation gap in terms of making it, written in Python, this accessible language, or making it work in like an interactive Jupyter notebook, and also some of the like lower level stuff, making sure that the Bluetooth connectivity with these devices is pretty reliable. So that's what this project's all about. Essentially, EEG Notebooks is just this series of Jupyter notebooks that have been kind of worked on over the years by a bunch of different people to test out primarily the Muse headband as a EEG research tool. And I want to start by going into like the history of the EEG Notebooks project, if that's all right with everyone, in order to kind of give credit where it's due to the people who came before me on this thing. So, yep, EEG Notebooks, accessible, affordable, and scalable cognitive neuroscience research platform. So the cool thing about this is that this whole project and the kind of supporting project behind it, which is the Muse LSL library, was just created by a bored brain-computer interface engineer who, for fun and in order to use the new 2016 model of the device that they released for his research, reverse engineered the Bluetooth protocol. So he was able to tap into the Bluetooth stream and get raw data. After spending a little while doing that, the first thing he did was then validate the P300, the most classic event-related potential that's used for brain-computer interfaces. And he wrote this great blog post that's still online. I recommend you check it out. It's just Alexandre Berachon, P300. He talks about a little bit of how he reverse engineered it and how he got the P300, and kind of compares it to like a research grade system. And in his hands, unfortunately, it works out pretty well. So, he did this all open source. All of his GitHub code was just there. Yeah.
Did you share your screen? Because I see.
Oh gosh, I forgot that. Here, make sure the screen get these slides up. All right, thanks, Sydney. Cool. Yeah. So it all started with Alexandre Berachon. He deciphered the Muse Bluetooth protocol and put all this code out in the open source. And then, interestingly enough, there was actually an intern who got hired at Interaxon, the company who makes the Muse headband, Ben Shapiro. And for his summer project with the company, he was tasked with validating a lot of these classic EEG phenomena for brain-computer interfaces and other uses. And he decided, just because the Muse LSL library was so easy to work with, that he was going to use that. And he started working in Jupyter Notebooks. And eventually, another researcher there, Hubert Bonvie, open sourced all the work that they'd done in-house. And they, in addition to the P300, added a bunch more EEG phenomena, the steady state visual evoked potential, steady state auditory evoked potential, auditory oddball, and a faces versus houses N170 ERP experiment. Now, these are all experiments. The ones that they chose were ones that would work specifically for the electrode configuration of the Muse. There's some things you can't do with the Muse, but what we want to do with EEG Notebooks, now that we've kind of maybe formalized the structure, is start adding in integration for other devices too. And so that brings me over to the kind of technology that we're using here. So Muse LSL was that library that Alexandre Berachon created. In the last couple months, I did some work cleaning it up and making it a command line interface, and also an importable module that you can use in other coding projects, which is how we use it in the notebooks. But the backbone of the Muse LSL library is just the lab streaming layer, or LSL streaming protocol, which is, as many people know, kind of like the gold standard in the EEG and BCI fields. And there's a ton of other EEG devices that have LSL drivers. In fact, most of the research grade EEGs have LSL software that they'll provide with you if you're a researcher using it. So Cognionics, ActiChamp, Biosemi, And the newer companies, mBrainTrain and Avertis, and of course OpenBCI have LSL plugins as well. So over the next couple months, we'd love to see some more experiments done with other devices. It should be pretty easy to get that first step of connectivity just using the existing LSL software, and that opens up the possibility of things we can do with the notebooks even more. If we get, parietal sensors, then we can do motor imagery and some more cool stuff. For stimulus presentation, for showing the images that drive the visual oddball experiment or the flashing gratings that are used in the SSVP, we use the PsychoPy toolkit, which is a pretty easy to use and friendly library for creating kind of psychology experiment stimulus presentation in Python. Really useful for this has been the M&E library for EEG data analysis. It's really full-featured and pretty easy to use, meaning that you can jump in and start doing things like, plotting PSDs and epoching your data, doing all kinds of transformations without having to, know how to implement all of those things yourself. And finally, we're using pretty standard matplotlib plus Seaborn combination for doing some of our plots. And the whole thing runs on Jupyter, which is really cool. There's some cool stuff coming up in the Jupyter ecosystem as well. Right now, I do most of my work with the notebooks in just the standard Jupyter Notebooks in the browser. But you can also run these notebooks in the Interact desktop application or the Jupyter Lab kind of IDE that they're coming out with. And I think there's also a possibility that we could get these notebooks running on the Binder backend for Jupyter as well, which is kind of an exciting thought. And so I said earlier, our goals were just to make it easier for people, who kind of heard about the promise of consumer neurotechnology, that they'd be able to learn more about their own brain, or they'd be able to do their own DIY research or build their own products. We want to make that easier to happen. And also, there's these two very real projects that a lot of the effort that's gone into EEG Notebooks has been supporting. There's the NeuroBright project here in Toronto. It's kind of a summer-long, or it's going to be a short-term experiential cognitive neuroscience program for high school students who are going to be learning about dementia while also doing their own EEG research in Python. It kind of combines learning about dementia, learning about neuroscience, and learning about scientific computing. And then there's the Brainwaves curriculum in NYU, which I've been working on recently, which is essentially an attempt to develop a full-fledged neuroscience course for high schools that can be delivered across the country. And as part of that project, we once again want kids to be able to run their own neuroscience experiments. So the EEG Notebooks has allowed us to really easily prototype the different types of experiments that we can do with cheap EEG systems like the Muse, and is kind of like guiding us as we build a more structured desktop application for the kids to use. And as I'm going to go and demonstrate one of the notebooks and kind of talk about the content, but keep in mind, this is an open source project and we're always looking for contributions. The top 3 things you could do would just be use the notebooks, give it your best shot if you've got a Muse, and if you have a good experiment, share your data. We're going to set up a system over the next week for merging PRs, pull requests, with data sets. And eventually we can combine that into the main repo and gather hopefully a pretty large data set of different users. And that could allow us to do some interesting things when it comes to machine learning and maybe developing processing pipelines for brain-computer interfaces. Also, if you're a researcher and you've got a favorite EEG phenomenon, or you've got some experiment that we haven't heard of yet, it'd be really cool if you can implement that in the stack that we've got and share it with us. And like I said before, if you want to add support for another EEG device, that would be awesome as well. You can kind of do that by getting in touch with us through GitHub. You can fork the project. It's just at github.com, NeuroTechX EEG Notebooks. And all of our discussion around this stuff is on the NeuroTechX Slack. And I recommend you join that anyway, because it's really helpful. going to move over to the notebook now. Oh, and so I've got one running here in Jupyter Notebook. But before I do this, I'll talk a little bit about the installation of the notebooks. Because we're trying to support all platforms, Mac, Windows, and Linux, and because there is this Bluetooth component there, and also a graphical component with the way we're presenting plots and the dependencies that go into the stimulus presentation, we've tried our best to streamline the installation process, and we have a step-by-step guide to installing and using the notebooks on Windows. But we know there are some bugs that exist out there, primarily in terms of different platforms requiring different dependencies, and sometimes some kind of behind-the-scenes installation and system fixes. Like for instance, on Linux, there's this common issue where you kind of have to give your Bluetooth system a message saying, hey, let the PyGat BLE library access the low-level driver stuff with like sudo authority. That kind of stuff is all over the place when we get into this kind of Python Bluetooth stack. But we've got a whole list of issues on the Muse LSL repo and on the EEG Notebooks repo that should make it as easy as possible. And you can also reach out to me on Slack or on GitHub, just post an issue if there's any issues. We recommend creating Anaconda environments because of all the dependencies that are required, and we'll be working on putting out an official EEG Notebooks Anaconda Python environment with all the dependencies preloaded to make it easier to get started. You can see here I'm going to be using a specific Jupyter kernel that I've set up ahead of time called Brainwaves. It's a Python 3 kernel with essentially the Muse LSL dependencies, the M&E dependencies, and a lot of the other stuff kind of figured out ahead of time. So the experiment I want to do today is the N170, which is the negative event-related potential that occurs about 170 milliseconds after you perceive a face. It's a cool ERP because it represents what we think to be higher level perceptual encoding, because it has this really similar pattern to what goes on in the fusiform face area, which has been studied relentlessly with fMRI. We think that it's really related to, not just perceiving like a nose or eyes or a mouth, but perceiving all of those elements in the proper configuration that represents a face. The other cool thing is that animal faces appear to elicit the N172. And the N170 is a really good ERP to get with Muse because it originates from the temporal and kind of temporal-parietal junction areas right around the ears. And that's exactly where the Muse's temporal electrodes TP9 and TP10 are. So we can usually get pretty good performance on this ERP with just one session even. So first I'll go back to my camera while I set up the for all of our experiments right now, you're going to need a Muse headband. Here's my Muse. It's like pretty much every other one. Importantly, it's a Muse 2016 device. And those are the only ones that are supported with the notebooks right now. The 2014s use an entirely different Bluetooth connection protocol. And we consider those deprecated. So I'm going to put on the Muse headband. It's on. The light was blinking. And now I can go back to my notebook and just run these cells that handle device searching and device connection right here. If you've got Muse LSL installed on your computer, you can just run these Muse LSL commands and start a process that streams data from the device in a terminal. But in order to make it easier and kind of make it totally self-sustained, we put those cells in the notebook. Interesting. Okay, so this first connection attempt didn't work. Give it another shot. Oh, my Muse turned off. Okay. All right, turning it on again. There we go. One thing I want to mention here is that on Windows 10, we have the ability to use another application for connecting to the Muse and opening an LSL stream. And that's the BlueMuse open source universal Windows platform app that one of the Neurotech Toronto members created. And we do recommend using that on Windows simply because it's the most reliable, and you can also connect to a Muse then without a Bluetooth dongle. On currently the Mac platform and the Windows platform, if you're not using BlueMuse, you have to use a dongle, and that's just kind of a pain in the ass. So we recommend BlueMuse, and also the support for LSL protocol is going to be coming to Muse's official Muse Direct app by the end of the summer. So at some point, hopefully no dongles for anybody anymore. So I've got a stream occurring right now with the Muse data. For the Python guys, this is actually like a background process that's going to be running. And yes, you can do that in Jupyter Notebooks. Next thing we'll do is we'll open a Matplotlib viewer that's plotting in real time the signals from the EEG device. Oh. Open it. Guys, let's see. Open the data inline, which often doesn't work, and this is probably due to the fact that this was written to support the Windows notebook. So I'm just gonna redo stuff here. Bear with me.
Maybe as you're working on that demo, I can ask some questions from the chat.
Oh, that'd be great.
Great. So give me a sec here.
There we go.
So one quick question, which I think was brought up by Mitch. What platforms is this supporting initially?
Yeah, so we've worked pretty hard to make sure that it works on all platforms. However, mostly because I'm a Windows and a Linux developer, the issue that we're having the most platform we're having the most issues with is Mac. If you're a Mac developer, please give EEG Notebooks a shot and let us know what bugs you run into. But theoretically, this should work on all systems.
All right, you're good. So I'll ask the rest of the questions later.
Cool. Yeah. Okay. So yeah, I don't know why the graph it came up inline at first. There's a little bit of an issue with the magic commands that you have to feed matplotlib. Sometimes it wants to pop up in the notebook, which doesn't work with real-time data. Sometimes it wants to pop up using a different backend that the platform might not support. There's a little note here. You have to use the TK backend on Windows 10. But we've got it running now, and you can see the real-time EEG data there is coming in. The signal quality actually looks pretty good. And if I stop talking, you'll see it get even better. We have this step here really importantly so that you can make sure that your signal quality is good enough before proceeding with the experiments. I'm going to full screen this for a sec. On the left side, the text might be kind of hard to see on the YouTube stream, but on the left side here, we've got the names of the channels. And yes, there's 5 channels technically in the Muse. This right aux channel is kind of an unused channel for now, but it would be where any extra electrode that you plug into the USB port, where that data would show up. And on the left here, these are just variance values, essentially standard deviation of the signal. We can't do an impedance check with the Muse, so we just go off standard deviation, and we try to encourage you to get that number below 10 before increasing. There was even an official study on replicating P300 done with Muse, and that's the variance values that they recommend getting below. So just to double check, I'm going to stop talking for a second and see if I can get my variance below 10. There we go. So when I don't blink, all the channels, including the temporal ones, which happen to be a little bit more noisy, was getting down to about 5 or 7. So that's good. Now let's run the experiment. First thing you're going to do as a user, this is pretty much one of the only things you would have to do if you want to do the cookie cutter like N170 experiment we've designed here, is modify these variables to define the parameters of the experiment. So experiment duration is the first one, although we always pretty much recommend doing 2 minutes. That's kind of the sweet spot between how much faces and houses being blinked at them and how many trials we can collect, we found. And subject and session ID, we recommend you define those yourself. We're working on a system right now to actually accommodate the BIDS, BIDS data standard for EEG and other like neuroimaging data storage. So this might be changing a little bit, but for right now, we can just define something like this. Subject can be a string or a number. Session should always be a number. So I'll call this Dano session 1. And now a little instruction here on how to run it. In order to get any of these experiments to work well, it's pretty important that A, signal quality is really good, and then there's no distractions, there's no background disruptions occurring when the participant's trying to take these things. So we really do encourage you maximize the possibility of success as much as possible. If you're going to run this experiment on someone who hasn't done EEG before, give them the whole talk, tell them that's really important. They keep their jaw and face relaxed, and they focus on the stimuli. For the faces and houses, it's really common to also give this additional instruction of mentally noting whether they're viewing a face or a house. And the following cell is just going to define a path to record to. And then it's going to start a process that will run the PsychoPy stimulus presentation and another process that's going to run a Muse LSL recording stream, which is just going to listen for the EEG LSL stream we have and record it alongside event markers generated by the PsychoPy stimulus presentation into a CSV file. So here we go. This is going to be a little bit boring for a second. I'm just going to try to do it, though, because I do want to demonstrate live one of the experiments here. So what you're going to see is just faces and houses appear interspersed by about like 1.5 seconds, and it's going to run for about 2 minutes. And I'm just going to be here wearing my Muse, focusing on the screen, try not to blink. All right. Oh my God. Okay, wasn't that fun? Yeah, it's live neuroscience on YouTube right now. I bet that doesn't happen too often. Yeah, so those can be a little bit grueling, and unfortunately, sometimes we recommend repeating them a couple times. If you can do that yourself 6 times, 2 minutes each, or get a subject to do it, you can usually get some pretty awesome data, even though it can be a little bit grueling. So make sure to kind of give yourself or the subject adequate breaks between them, and maybe give them a candy at the end or something like that. We'll see how that data went, and if it doesn't work, I can show you guys a pre-collected data set. So that's basically it. We've collected this one CSV file in subject Dano session 1 folder. That's going to be right in the main repository, and you can open it up, and it's just kind of like a really simply formatted CSV file with the header, channel values, and then the data. So next, we're going to load that data into M&E objects and start the analysis. So this next function, we use a lot of util functions that hopefully aren't too abstracted. If you want to take a look at what's going on, you can just go into the notebook/utils folder. We're going to load that data. And yes, we've got one raw array corresponding to about 120 seconds. So that's perfect. There are 5 channels. Looks good. The first thing I like to do is just plot the entire PSD of that data set. And it's super easy with M&E. Raw.plot PSD. Show it in line, and we'll see what that looked like. And ooh, that's pretty good. You can see big peak at 60 hertz from my background electrical activity. A little 50 hertz peak here. That's kind of interesting. Don't know what that is. That's from these 2 down here are the frontal channels. There's a blue channel here and then a green channel, which is honestly really hard to see. But the black and red are the temporal channels. Those are the ones we're most interested in. The thing you can do mostly here is kind of check if this is too furry, there's too much up and down, or if it doesn't have this kind of natural EEG shape with a peak at the lower frequencies, then it might mean that your channels were not making good connection. Next, we're going to filter this. We really only need like 1 hertz to 30 hertz in order to see the ERPs. That is super easy to do once again in M&E, just raw.filter 1 to 30. We're doing the IAR because it's a little bit better than the FIR filter, and we don't need to do this in real time. And look at the PSD once again, and yeah, it looks all right. It's just 1 trial, so it's a little bit noisier than I would like. We can't like average out the noise too much here, but maybe it'll work. Let's see. Next, we're going to do epoching. If anyone doesn't know what this is basically where we break up this big continuous EEG data set into little chunks. And we center those chunks around 100 milliseconds before to 800 milliseconds after each stimulus. And we can define that in the M&E epochs function as just T minimum and T maximum. So -0.1 to 0.8 is 100 milliseconds before, 800 milliseconds afterwards. And the data set has these event IDs saved in it. The last column actually is like an event marker column. And in there, we've stored house as 1 and face as 2. So whenever the epoching function sees one of those IDs in that last column, it'll create a new epoch 100 milliseconds before and 800 milliseconds afterwards. So we run this. We can see how many events we collected. So there was 50 faces and 52 houses. We can also calculate the percentage of samples that were dropped. What I failed to mention was we also have the opportunity in the epochs function to reject epochs that have an amplitude over a certain amount. And it's not the most sophisticated artifact rejection, but it lets us get rid of most blanks at least. And so we lost about 4.6% of the data to blanks, which is totally reasonable. That's actually a great number. If you get above 15, and definitely if you get above 20, then I'd say consider going back and re-recording the data set. And so now we've got all these epochs representing the EEG that happened basically right after a face or a house was presented. So now we can just basically average all of those epochs and see what the average EEG response to looking at the stimuli was. Oh boy. Okay, this looks great actually. So you can see we've got all 4 channels, and this is how they're arranged around the head and the muse. You've got your left ear, your left forehead, and right ear. And there's quite a bit of noise here, which makes sense because this was a pretty small data set. We collected, we weren't able to average over too much to get rid of the noise. However, we're looking for a negative deflection around 170 milliseconds after stimulus onset, and I do believe I see a pretty great one right here at the TP9 channel. So house data is in red, face data is in green. We also have this kind of difference waveform right here, which can help also illustrate, the difference specifically between the face and house condition. And yeah, that deflection down there is pretty good. You can see it kind of mirrored on the right channel, but not as strong. And this is an interesting thing I'd love to throw out to any neuroscientists out there. We see this all the time with the Muse and the N170. Sometimes we only see it in the left hemisphere. And I don't know exactly why that is. I'm a right-handed person. Maybe my facial recognition networks are laterally localized, but I don't know. This is pretty exciting, though. We'll go on and we'll actually run some machine learning on this data set in order to kind of objectify how accurate or how clean this data set was, and whether we could use this data set to train an N170 classifier. So there's a bunch of different machine learning pipelines implemented in scikit-learn and M&E and the PyRiman library, which weren't created by me, so I can't go too deep into the actual computation going on here. But essentially, it's a collection of different approaches for processing and classifying EEG data, such as would be used in a brain-computer interface. We've got 4 different options here, including basically a different mix of vectorization, logistic regression, and then like least linear discriminant analysis, as well as 2 kind of Riemannian geometry-focused pipelines created by Alexandre Berchamp using tangent space mapping, and then this other thing called MDM, which I forget what that is. But these, the Riemannian geometry approach, I recommend you look into PyRiman and the work of Alexandre Berchamp if you want to learn more. Essentially, it has the potential to remove a lot of the sources of noise in EEG and also produce classifiers that are going to be more applicable to multiple different people, because apparently mapping the EEG signal into this higher Riemannian tangent space can remove a lot of the peculiarities of the EEG signal. So these are already implemented for you, so you don't got to worry about doing too much. If you want to implement your own scikit-learn pipeline here, this would be the spot. But simply, we define a bunch of pipelines, standard scikit-learn stuff. We format our data in the right way, get our X and Y matrices. And we're going to do a cross-validation with an area under the curve estimate to try to see how accurate these guys are. And it's a little while to run because this is machine learning after all.
So maybe we can do one more question as it's running.
Yeah, sure. It's done, but
okay, one quick question then. So someone posted this a little bit earlier, but I don't know if they got a response. So maybe you have a good answer for it. Someone was wondering if there's another program similar in Toronto to the NeuroBright one, or is that the only one that you know of?
The NeuroBright program is the only one I know of specifically in Toronto. Yeah. If they're maybe thinking of something, I'd love to learn if there are any other programs like that, because I'd love to help out.
Okay, great.
Okay, cool. So we've got all of our classifiers trained. Oh, I forgot also forgot to mention, there are these two other ones here, XDON covariances and XDON with MDM. Let's just plot all of the performances. Now we'll kind of run these classifiers on our data and see how well they do. And oh my gosh, so they're all pretty much in the same ballpark, but you can see some are better than others. The ERP covariance plus tangent space projection seems to be doing particularly well. That's the Riemannian geometry one, so that's not too surprising. But what's nice is these are getting around 0.8 area under the curve, which, you know, a bit of an oversimplification, you know, at least in my brain, kind of suggests 80% accuracy from a single trial of classifying whether that's a face or a house epoch. And so that's pretty good. Very good, in fact, for just a 2-minute data collection. It's one of the best I've gotten. So the demo day effect didn't really kick in, which is nice. So that's essentially the notebooks. We have the same format for all of the different experiments, where, you know, you can connect to the Muse right in the document. You can run the stimulus presentation, run that analysis, get your ERP graphs, and then do the that little machine learning step at the end. And you know, if you work through that, and if you have some good stuff that happens, then we do recommend sharing your data. Just make a pull request with ideally just the data sets and not the notebook in particular. We kind of want to keep these notebooks pretty boilerplate and standard. And yeah, that's basically it. So it took me like, what, 10 minutes to do that? And a pretty cool little bit of science just happened here. Just finish off by saying, yeah, so we've got a couple other notebooks that are available. The ones that we have implemented and ready to go right now for you guys, if you want to take a look, are basically the ones that we know work best with the Muse, the N170 that I just demonstrated, the P300, which will be a visual oddball task where you're looking at different orientations of gratings, or if you want cats or dogs, and then the steady state visual evoked potential, which I should talk about a little bit. So this one is kind of this is a fun one because it doesn't work too well with the temporal electrodes, the built-in ones, but we actually recommend using this extra electrode right here. They're a cool way to kind of make the Muse like a more legit research tool. Depending on how long you make that cable, you can get up to parietal cortex, you can definitely get occipital cortex, and it can really like make some projects possible that wouldn't be possible otherwise. Downside is they don't officially sell the extra electrodes. So you have to make it yourself or get in contact with the company. I can help you do that if you reach out to me, and then maybe they'll build one for you for a fee. But when you use this one with the SSVP, you can get really killer performance because the SSVP is an occipital lobe phenomenon. So here's an example. This is what the two power spectral densities of like a 30 hertz and a 20 hertz stimulation will look like with the temporal electrodes. So you can see these tiny little peaks at 20 hertz and 30 hertz. And then boom, the parietal occipital electrode placement gets you, about 4 times the amplitude, and so a lot better signal noise response. You can even see the harmonics of the 20 hertz stimulation as well. And so that's basically it for demoing the EEG notebooks. There's a couple that we have kind of in the pipeline, old experiments that Alexandra and Ben did back in the day that we haven't converted to this new format yet. And we're going to be working on getting those going soon. One of the cool ones there is the steady state auditory evoked potential, which apparently works especially well with the Muse.
So I have a couple questions for you.
Cool.
From chat.
Yeah.
And, please, people, if you do have any questions you want to ask, please do so now. So the next one that I had was, is there interest in having this in a mobile/tablet environment at all?
Yeah. So first off, Well, unfortunately, so we've had a lot of issues getting this running on Windows tablets because they have like a different CPU architecture. They just don't seem to handle the Bluetooth connection strategies we're using. And so unfortunately, we're not going to focus on tablet or mobile support for EEG notebooks. That said, EEG 101 is an Android app and soon to be an iOS app that can teach the basics of EEG and signal processing, and also let you run your own little brain-computer interface that you can train with your own data. And it could also be used as a research tool. There we have CSV data recording and a bunch of different kind of pre-processing stuff you can do. But yeah, just because it's been really hard getting this working on tablets, and also EEG Notebooks is focused towards more hackers or students who are going to be kind of forking it and extending it on their own. We're not going to be focusing too much on that.
Related to that question by the same person, on the mobile thing, is there interest in this or for other languages, not just Python, so you can support more platforms?
Well, Python does seem to be kind of the most popular scientific language and data science language, so we're really focused on that. There is some cool source code for doing EEG stuff like this in C# with a Windows app. But as far as EEG Notebooks goes, we're firmly in the Python world.
So Mitch just replied in chat, and he said that his specialty is in the mobile side. So if you're looking for any support on that, you could always reach out to him. Next question, so this is more of a general question related to the Muse device. Yes. Is there ways in making the Muse Bluetooth more reliable? For at least this individual, that's always been the hardest part.
And he's totally right. That's always the hardest part. I would recommend them making sure that they're using the newest Muse LSL library version, because I've been working really hard on fixing all the issues with that and making that work as well as possible. But there's still a ways to go, especially on Mac. Once again, if you're a Mac developer and you have a Muse and you want to help out, even just kind of giving it a try with like a fresh computer and posting all the steps that you have to follow or any bugs you run into would be really helpful. The other thing about that, though, is kind of because of like EEG Notebooks and because of the work that Ben Shapiro did inside Interaxon, they've realized that LSL is going to be an important thing for them to support. So they're working internally on using LSL in their standard Muse Direct Windows app. So when that comes out, when that feature comes out, hopefully, the Muse Direct app with the LSL output is going to be kind of the gold standard Muse connection process, at least for Windows. Linux and Mac, Muse LSL still might be the best way. But at least when that comes out, hopefully that should solve a lot of the existing issues with Bluetooth connectivity.
So once again, a more general question about the Muse device. Isn't the Muse limited on the locations where it can pick up signal?
Yes, absolutely. It's only got those 4 electrodes. If you want to do stuff with parietal sensors or more advanced like frontal sensor configurations, you're not going to be able to do it. But you can, if you build an extra electrode, get one more electrode placement, and that might be enough for your project. But also, there are other EEG devices out there, and you could use those. Emotive or OpenBCI would be pretty easy to get started with, and it's all about kind of the trade-offs too. The EEG Notebooks experiments that we've vetted and have kind of written code for, they do seem to work pretty well with the limited electrode placement of the Muse.
And another question, so which other metrics would you recommend to evaluate machine learning algorithms on classifying P300 events? So they give a few examples: recall, logarithmic loss, F beta, et cetera, et cetera.
That's well, I wouldn't want to make up stuff, so I wouldn't know enough to come up with a better recommendation than when it sounds like they've already got some good ideas about. However, this area under the curve metric seems to be the one recommended by Alexandre Bertrand, who's kind of the expert in this EEG machine learning field. So I pretty much stick with that. Yeah.
All right, another question. What about reproducing with OpenBCI or Emotive? Have you kind of thought about that?
Absolutely, yeah. So like I said before, that would be really cool if we could get more EEG devices working with this. And the steps to do that would basically be, number one, get a LSL stream going with the software available for those devices. The OpenBCI has a Ganglion LSL and a Cyton LSL library that's available on GitHub. Once again, it's open source. Emotive doesn't have official LSL support, but I think there has been a couple people who've tried to do that over the years. That would be a little bit harder though. But yeah, so support for another EEG device would be simple as just using whatever software is out there to get an LSL stream open, and then walking through the notebooks, maybe changing parameters here or there related to like electrode names, or the size of different arrays, and the number of plots. It should be pretty easy to just kind of rewrite some of the code at a pretty high abstract level and have it work entirely similarly as it does for Muse.
So another question we have, like maybe going around the topic of the use of Python, why did you go with maybe Python versus like MATLAB, considering that, there's a bunch of things that MATLAB supports, like EEG Lab, Brainstorm, that can help with EEG data, versus maybe something like the BCI 2000 and this language that it uses, C++.
Absolutely. Well, it's a little bit of personal preference. I've always worked in Python. Even when I was a scientist, I was doing Python, and I know there is a movement, at least in the the sector of the world, where open source software and scientific research kind of overlap. Those guys are moving towards Python. The cool thing too is Python's also a pretty suitable language for some BCI work too, at least in terms of like prototyping and like early stage development and research. And it's also a language that can be, deployed reasonably well on the web. I was talking about Binder earlier, which is essentially where you can have a server that will run your Python code for someone who's working with a Jupyter Notebook in the browser. So, we could maybe, because we're using Python, get to a point where students in the NeuroBright program can just show up to a computer lab in their school, just go to a website, like a link their teacher posts on a chalkboard, and then start doing these EEG experiments with M&E and all of the Jupyter stuff handled right there. And yeah, because Python's just more flexible and gives us more kind of opportunities down the road, we've stuck with that.
So what's the difference between the 2014 and 16 Muse?
Okay, yeah. So the first thing is there's pretty much nothing different in terms of the actual like structure and hardware of the thing. They did remove a USB port in the 2016 Muse, so it's only got one charging port and one auxiliary electrode port. I mean, those are the same, one and the same. But so the electrode placement, the sensitivity of the electrodes is all the same. What they did in the 2016 was increase the sampling rate. Well, the main thing they did was switch from Bluetooth 4, I believe, to like a classic Bluetooth chip to a Bluetooth low energy chip. And also because they did that, they increased the sampling rate from 250 hertz to 256 hertz, or 230 hertz or something like that. 256, I should know that. But yeah, so this big switch from Bluetooth 4 to Bluetooth low energy was great for the device because it means it has basically 10 times the battery life. If you do use a Muse 2014, you know that it runs out of battery pretty quick. And it's also easier to connect to. Device discovery and initiating connections is a bit easier on Bluetooth low energy. But unfortunately, it does mean that the libraries, like the software libraries, what we use in Muse LSL and EEG Notebooks to connect to the Muse is totally different. We're not using standard Bluetooth. We're using specific Bluetooth low energy libraries. Specifically with EEG Notebooks, we're using PyGat, which is a Python-based Bluetooth low energy library. And yeah, that's basically it. So Bluetooth low energy, reducing the device ports, and keeping the rest of it the same. But it means it's very different for software developers to work with.
One question for people that may not have a Muse: is there a way that they can rerun scripts, analysis, and plots with fake or pre-recorded data?
Yeah.
Quickly, but could you elaborate a little bit more?
Yes, absolutely. Let me jump back to the notebook a little bit, if I still have it. You can see the notebook. Okay, so kind of like I said in the notebooks, all these recording cells are doing is creating a CSV file in the main repo. And we have a ton of data that we've collected over the last year that's just comes in the repo. So if you want to just do the analysis stuff and you don't have a Muse to collect your own data, all you got to do is load one of these notebooks and basically skip right to step 4. Whatever subject and session ID you've defined in this cell up here will be the ones that are loaded into the notebook and analyzed. So you can select, subject 1, session 1, for instance. That's our standard, kind of like gold standard data set that we've managed to collect. So all we got to do is load that. And now we've got this whole data set of EEG we can work with and do all the analysis and even the machine learning with. So there's definitely a lot of utility even for someone who doesn't have their own EEG to do at least the analysis stuff and maybe prototype their own pipelines or way of looking at the data.
So we're almost done here, so we'll do 2 more questions. Next one is, how accurate are the timestamps of the Muse packets, and is there any kind of correction done tied to that? How would you go about integrating other signals such as webcam feed or other forms of signals?
Yeah, okay, first off, Muse timestamping, that's been an issue that we've worked on a lot over the last 3 months, or 5 months, more like. There's still one kind of unsolved issue where there's a delay between when we send a message to the Bluetooth to start streaming and the Bluetooth kind of activates its own internal streaming and then sends a packet back. And that will vary in between connection sessions. And so we haven't been able to come up with a way to really convince to kind of lock that down and get that out of the way. But we've gotten over a lot of other issues that have popped up in the last couple months. So what's occurring right now in Muse LSL and EEG Notebooks is the best, I think, basically, the best that you can do as it stands. Essentially with the Muse, that means there's around a 40 millisecond delay, plus or minus with a jitter of about 5 milliseconds. And that seems to be good enough for most of the event-related potential experiments we're doing. I guess the other part of that question was about other data types and other markers. That's pretty easy to do with the LSL protocol, fortunately. All you would have to do is, set up a webcam system or some other maybe an eye tracker system, and then just make sure that that is outputting timestamp data in the same network as like an EEG Notebooks project. And maybe with a little changes to our Muse LSL recording function, you could also listen in for eye tracking or webcam stream data and then save that into the same CSV file. So it's totally possible, and I recommend giving it a shot.
Cool. And last question. So what should we expect out of this project for the next couple of months? And if people are wanting to help, how do they do so, and what skills do they need?
Yes. Okay. Let me go back to my little slide here. Things you can do for EEG notebooks. Oh gosh, that's going in the wrong direction. There we go. So over the next couple months, we are going to be doing some more iteration in order to clean things up for the NeuroBright project specifically. We're working on making things work even better in Mac, and we'll be getting a lot of design feedback from kind of our target demographic for NeuroBright, at least, which is high school students, and introducing those lessons back into the project. The things that the open source community could do for us would be collect data and bring it back into the main repo. We do want to build a larger and larger data set that people can look at, and then also add more EEG experiments and device support. The skills that you would need to do that would be essentially, I mean, besides maybe some neuroscience experience, particularly for adding an EEG experiment, just basic Python developer skills. We've done a lot of the tricky stuff, kind of like the hard work of figuring out how exactly to get this Bluetooth and the stimulus presentation working together in Jupyter. So hopefully anyone who can, write a Python script and maybe, figure out how M&E works, which is pretty easy, could, do some tweaks to one of our existing stimulus presentation scripts to create a new experiment, and then, work off our existing M&E analysis code as a model to analyze that data in the way that they see fit. And it shouldn't honestly be too hard, but it is a little bit of Python coding for sure.
Awesome. Well, I think that pretty much wraps it up. Thank you very much, Dano, for presenting your work. It's really some awesome and fascinating stuff. And I'm really glad that we finally have this great tool that will really help to expand the accessibility into the field of EEGs and neurotechnology.